New research published in Classical and Quantum Gravity suggests that wormholes, as commonly imagined, may not exist at all. Instead, scientists argue that the famous Einstein-Rosen Bridge points to a deeper structure in physics, one connected to time itself rather than space. The study reframes this long-standing idea as a quantum link between two opposite directions of time, not a tunnel through the universe. In this exploration, we will examine what this discovery means, why it matters, and how it could fundamentally change our understanding of time in the universe. Let's begin. The concept at the heart of this research originates in 1935, when Albert Einstein and Nathan Rosen introduced what they called a bridge in spacetime. Their work was not concerned with travel through space or shortcuts across the universe. Instead, it addressed a technical problem in theoretical physics: how to describe particles and gravitational fields consistently in regions of extreme gravity. The Einstein-Rosen Bridge was a mathematical construction linking two perfectly symmetrical versions of spacetime. It was designed to preserve consistency in physical equations, not to represent a physical structure that could be crossed. In its original form, it was neither observable nor intended to correspond to a real object in the universe. Decades later, this idea was reinterpreted. The term wormhole emerged, and the bridge began to be described as a tunnel through spacetime. Over time, this interpretation spread through theoretical physics, popular science, and science fiction. Wormholes became imagined as gateways between distant regions of space, or even as paths through time. However, even within Einstein's own theory of general relativity, these structures were never physically viable. Mathematical models showed that such bridges would collapse too quickly for anything to pass through them. They would pinch off faster than light could travel, making them non-traversable and unobservable. In practical terms, they remained abstract solutions, not physical objects. The new research revisits this original concept using a modern quantum perspective. Instead of treating the Einstein-Rosen Bridge as a spatial structure, the researchers reinterpret it as a quantum structure. In their framework, the bridge does not connect two places in space. It connects two components of a quantum system. Specifically, it represents two opposite directions of time. One component of the system evolves forward in time, while a complementary component evolves backward from a mirror-reflected position. Both components are necessary for a complete quantum description of reality, particularly in extreme gravitational environments. In this interpretation, the bridge is not a tunnel. It is a mathematical connection between two time directions. It reflects a deeper structure in how quantum systems behave when gravity becomes significant. This reframing changes the meaning of the Einstein-Rosen Bridge entirely. It is no longer a misunderstood attempt at building a cosmic shortcut. It becomes a model of time symmetry at the quantum level. The familiar idea of wormholes in this context is not just speculative. It is conceptually misplaced. What the mathematics actually describes is not movement through space, but structure in time. To understand why this reinterpretation matters, we must first explore the foundations upon which it rests. The universe operates according to laws that have been tested and refined over centuries of scientific investigation. These laws govern everything from the motion of planets to the behavior of subatomic particles. Among these fundamental principles, one stands out as particularly profound: the symmetry of time in physical equations. This symmetry reveals something extraordinary about the nature of reality itself, something that our everyday experience obscures, but that mathematics makes clear. At the deepest level, the laws of nature do not distinguish between past and future. If time is reversed in the equations of quantum mechanics or general relativity, the equations remain valid. Time symmetry is built into the foundations of physics. This means that for every process that can occur moving forward in time, there exists a corresponding process that could occur moving backward in time. The equations themselves are indifferent to the direction of temporal flow. They work equally well whether time moves from past to future or from future to past. Yet, our experience of time is one-directional. We move from past to future. Causes precede effects. Disorder increases. Memories form of events that have already happened, never of events yet to come. We age. We never grow younger. Broken eggs do not spontaneously reassemble themselves. This arrow of time feels so fundamental to our existence that it seems impossible to imagine reality functioning any other way. But here is the remarkable truth. This arrow of time is not fundamental. It emerges from thermodynamics, entropy, and large-scale physical systems. It is a statistical phenomenon, not a law written into the fabric of space-time itself. Quantum mechanics does not require preferred time direction. At the microscopic level, physical processes can be reversible. An electron scattering off a photon could just as easily be described as occurring in reverse, with the mathematics remaining perfectly consistent. The same applies to gravitational interactions in general relativity. A star collapsing under its own gravity obeys equations that are time-symmetric. The mathematics allows for both collapse and expansion, both forward evolution and backward evolution. The new research takes this symmetry seriously and applies it to gravitational systems in a way that has profound implications. The central claim is that a complete quantum description of reality must include both time directions. A forward evolving component and a backward evolving component together form a full physical system. This is not merely a mathematical trick or a convenient framework. It is a statement about the fundamental structure of quantum reality in gravitational contexts. In everyday physics, one time direction is selected because macroscopic systems are dominated by entropy and irreversibility. When you observe a system with trillions upon trillions of particles, the overwhelming statistical tendency is for disorder to increase, for heat to flow from hot to cold, for complex structures to decay into simpler ones. This thermodynamic arrow of time emerges from the sheer number of particles involved and the statistical mechanics governing their collective behavior. It is why we remember the past but not the future, why we observe effects following causes, why the universe appears to have a temporal direction. This simplification works under normal conditions. For most phenomena we encounter in daily life, for most laboratory experiments, for most astrophysical observations, treating time as flowing in one direction is perfectly adequate. It produces accurate predictions and allows us to understand the world around us. But in extreme environments, this simplification may fail. Near black holes, in strong gravitational fields, or in the early universe, the conditions become so unusual that our ordinary assumptions about time may break down. In those conditions, both time directions become necessary for consistency. The forward evolving component and the backward evolving component must both be included in the description of physical reality. Neither can be neglected without losing essential information about the system. The Einstein-Rosen Bridge emerges as the mathematical structure that links these two components. It is not an optional feature. It is required for quantum completeness and reversibility. This is a stunning realization. What was once interpreted as a hypothetical tunnel through space is now understood as a necessary feature of quantum systems under extreme gravity, a feature that connects not distant regions of space, but opposite directions of time. The bridge is not something that might exist under special circumstances. It is something that must exist whenever we properly account for quantum mechanics in strong gravitational fields. This perspective also offers a new way to think about one of the most troubling puzzles in modern physics, the black hole information paradox. Traditionally, black holes appear to destroy information, violating a core principle of quantum mechanics that information must be preserved. In quantum theory, information about a system's initial state is never truly lost. It may become scrambled, dispersed, or encoded in complex ways, but it remains recoverable in principle. The total information content of the universe should remain constant. Black holes seem to violate this principle. When matter falls into a black hole, it appears to disappear from our universe. As the black hole evaporates through Hawking radiation, the radiation that emerges seems to carry no information about what fell in. The information appears to be destroyed, creating a fundamental conflict between quantum mechanics and general relativity. Physicists have proposed numerous solutions to this paradox over the decades, but many involve exotic physics or speculative mechanisms. This paradox arises when physics assumes a single one-directional flow of time extending through the event horizon. We imagine time flowing forward as matter crosses the point of no return, continuing forward inside the black hole, with information carried along that forward-flowing timeline until it reaches the singularity and is presumably lost. But if both time directions are included, the paradox disappears. Information does not vanish. It leaves our time direction and continues evolving along the opposite one. From our perspective, observing the universe from within the forward-flowing time direction, it appears lost. We cannot access information that has transitioned into the backward-flowing component of the quantum system. But from a complete quantum perspective, one that includes both time directions, the information is conserved. It has not been destroyed. It is merely moved into a component of reality that we cannot directly observe because we exist within a single time direction. This resolves the paradox without introducing exotic matter, speculative particles, or modifications to known physics. It relies only on time symmetry and quantum reversibility, principles already established in physics. The solution emerges naturally from taking seriously the idea that complete quantum descriptions require both time directions, especially in extreme gravitational environments like black holes. The reinterpretation also fits into broader efforts in quantum gravity, where time itself becomes a problematic concept. Many models suggest that time is not fundamental but emergent, a property that arises from deeper structures. Just as temperature emerges from the average motion of particles, or just as pressure emerges from countless molecular collisions, time might emerge from something more fundamental. This research aligns with that view by treating time, direction, as a macroscopic feature rather than a microscopic law. In this framework, the Einstein-Rosen Bridge becomes a mathematical expression of temporal symmetry rather than a physical object. It reflects the structure of quantum evolution under gravity, not a geometry for travel. It is a statement about how quantum systems must be described when gravity is strong, not a prediction about tunnels that could be traversed. The implications of this work extend far beyond wormholes and black holes. If the interpretation is correct, it changes how we think about the origin and structure of the universe itself. One of the most significant possibilities is that the Big Bang may not have been the absolute beginning of time. Instead, it may have been a quantum transition, a bounce between two time-reversed phases of cosmic evolution. In this scenario, a contracting universe transitions into an expanding one with time-reversing direction at the boundary. Imagine the universe contracting, growing smaller and denser, approaching what we call the Big Bang singularity. In conventional cosmology, this singularity represents the beginning, the point before which nothing existed, not even time. But in the time-symmetric framework, the singularity becomes a transition point rather than an absolute origin. On one side of this transition, the universe contracts with time flowing in one direction. On the other side, our side, the universe expands with time flowing in what we perceive as the forward direction. But these two phases are connected. They are two components of a complete quantum cosmological system. The Big Bang is not a beginning, but a boundary condition, a quantum bounce where one phase transitions into another. This would mean that our universe could be the continuation of a previous cosmic phase, not the first one. The Big Bang becomes a transition point rather than a starting point. This idea is not entirely new in cosmology. Bouncing universe models have been proposed before, attempting to avoid the conceptual difficulties of an absolute beginning of time. What makes this new interpretation distinctive is how it grounds the bounce in the time-symmetric quantum structure represented by the Einstein-Rosen Bridge. In this picture, black holes are not spatial tunnels, but temporal boundaries. They connect different time directions rather than different locations. They are not shortcuts across space. They are transitions across time. When matter falls into a black hole from our perspective, it is transitioning from our forward-flowing time direction into the complementary, backward-flowing direction. The event horizon is not a barrier in space, but a boundary between temporal components of the quantum system. This is a radically different way of thinking about black holes, but it emerges naturally from taking time symmetry seriously in quantum gravity. It suggests that black holes play a role in the structure of time itself, not just in the geometry of space. They are features of temporal architecture, not spatial topology. The theory also opens the door to observational tests. If time-symmetric quantum structures exist, they may leave measurable signatures in cosmology. Subtle asymmetries in the cosmic microwave background, the faint afterglow of the Big Bang that fills the universe, could provide clues. These asymmetries might reveal imprints of the pre-bounce phase, traces of the time-reversed component that preceded our expanding universe. Anomalies in large-scale structure, the distribution of galaxies, and galaxy clusters across cosmic distances could offer another avenue for testing. If the universe underwent a quantum bounce, rather than emerging from an absolute singularity, the patterns we observe in the distribution of matter might differ subtly from what conventional Big Bang models predict. Detecting these differences would require extraordinarily precise observations, but they are not impossible in principle. Unexpected relic objects could provide indirect evidence. If a pre-bounce phase existed, some remnants from that phase might have survived the transition. These would appear in our universe as anomalous objects, things that do not fit neatly into the standard timeline of cosmic evolution. Some speculative models suggest that certain forms of dark matter could consist of remnants from a pre-bounce universe. Dark matter makes up approximately 85% of all matter in the universe, yet we have never directly detected it. We know it exists because of its gravitational effects on galaxies and galaxy clusters, because of how it bends light through gravitational lensing, because of its influence on the cosmic microwave background. But we do not know what it is. Countless experiments have searched for dark matter particles, but none have definitively detected them. What if some portion of dark matter consists of remnants from the time-reversed phase before the Big Bang bounce? These remnants would interact gravitationally, but might have unusual properties reflecting their origin in a different temporal component. They might not interact with ordinary matter in the ways we expect, explaining why direct detection has proven so difficult. This remains highly theoretical, but it offers testable directions for future research, rather than pure speculation. What makes this framework significant is not that it promises dramatic technologies or science fiction outcomes. It does not bring us closer to building time machines or traversing the cosmos through wormhole shortcuts. Those fantasies remain as distant as ever. What it offers instead is something more profound, a coherent way to connect quantum mechanics, gravity, and time without breaking known laws of physics. It removes the fantasy of wormholes as cosmic tunnels, but replaces it with something more fundamental, a universe where time itself has a deeper structure than we perceive, where our experience of flowing from past to future is only one component of a richer temporal reality, where the mathematics describing extreme gravity points not to shortcuts through space, but to the intrinsic structure of time in quantum systems. This reframing forces us to reconsider what we mean by fundamental questions. What does it mean for something to exist in time? What does it mean for time to flow? Are these questions about objective features of reality? Or are they questions about how macroscopic systems like ourselves, composed of countless particles and dominated by thermodynamic irreversibility, experience a quantum universe that is fundamentally time-symmetric? The philosophical implications are profound. Our intuition about time is shaped by our macroscopic experience. We exist as complex, thermodynamically driven systems, embedded in a universe where entropy increases. Our consciousness, our memories, our sense of causation, all depend on this thermodynamic arrow. We cannot help but perceive time as flowing from past to future, because that is the direction in which entropy increases for the systems we are part of. But the universe, at its most fundamental level, may not share this directional character. The equations governing quantum mechanics and gravity are reversible. They permit both directions of time equally. The new research suggests that in extreme gravitational environments, both directions must be included for completeness. Our one-directional experience is a special case, valid for macroscopic systems under ordinary conditions, but inadequate for describing reality in its full quantum generality. This challenges the notion of time as an absolute background against which events unfold. Instead, time emerges as a feature of how quantum systems evolve, and in strong gravity, this evolution has a richer structure than our intuition suggests. The Einstein-Rosen Bridge, once thought to represent a tunnel through space, becomes a symbol of this richer temporal structure. Future research will focus on refining these models, connecting them to observable physics, and testing whether time-symmetric quantum structures can produce measurable effects in astrophysics and cosmology. Theoretical physicists will work to develop more detailed mathematical descriptions, exploring the consequences of time-symmetric quantum gravity for black hole physics, cosmology, and the fundamental nature of space-time. Observational astronomers and cosmologists will search for signatures in data, looking for subtle anomalies that might distinguish time-symmetric models from conventional ones. Particle physicists will consider whether time-symmetric structures could explain features of dark matter or other mysterious phenomena. The theory will ultimately stand or fall based on its predictive power and empirical consistency. Wormholes may not be real physical structures in the sense that science fiction imagined. They may not offer shortcuts to distant stars or pathways to other universes. But what they reveal is something deeper and potentially more remarkable: a fundamental symmetry in time itself. This symmetry has always been present in the equations of physics, but its full implications for quantum systems in strong gravity are only now being understood. This could reshape how we understand the universe at its most fundamental level. It could change how we think about black holes, not as objects that trap and destroy, but as temporal boundaries connecting different components of quantum reality. It could change how we think about the Big Bang, not as an absolute beginning, but as a quantum transition between time-reversed phases. It could change how we think about the nature of time itself, revealing that our one-directional experience is a special case of something more general. The journey from Einstein and Rosen's original bridge concept to this new interpretation spans nearly 90 years of physics. It illustrates how scientific understanding evolves, how ideas are reinterpreted in light of new frameworks and deeper insights. The mathematics of 1935 remains valid. The equations have not changed, but their meaning has been transformed by applying quantum principles and taking time symmetry seriously. What began as a mathematical solution to a technical problem in general relativity became a science fiction staple, then returned to physics as something entirely different: a window into the quantum structure of time in extreme gravity. This evolution reflects the nature of theoretical physics itself, where mathematical structures often point to truths about reality that transcend their original context. The Einstein-Rosen Bridge may never allow us to travel through space, but it may allow us to travel through our understanding to reach deeper insights about the universe we inhabit. It reminds us that reality at its most fundamental level often defies our intuitions, shaped as they are by macroscopic experience. The universe revealed by mathematics is stranger and more subtle than everyday perception suggests. Consider what this means for our cosmic story. For decades, we have imagined the universe beginning at the Big Bang, time itself springing into existence at that singular moment. Before it, nothing. Not even the concept of before makes sense if time itself began at the Big Bang. This has always been philosophically troubling. How can something emerge from nothing? How can time itself have a beginning? The time-symmetric framework offers a different narrative. Time does not begin. It transitions. What we call the Big Bang is a boundary between two phases of quantum evolution, one contracting with time flowing in one direction, one expanding with time flowing in what we perceive as the opposite direction. The universe is not created from nothing. It transitions from one temporal phase to another. This resolves some philosophical difficulties, but introduces new questions. What determines the transition? Why does the bounce occur? What physical mechanism governs it? These questions do not yet have complete answers. The mathematical framework is still being developed, but the fact that these questions can be posed in a physically meaningful way, grounded in established principles like quantum mechanics and time symmetry, represents progress. It shifts the mystery from how can something come from nothing to what governs quantum transitions between time-reversed phases, a question that can be approached through physics rather than metaphysics. It transforms the origin of the universe from an impenetrable singularity into a phenomenon that might be understood through quantum cosmology. The implications ripple through our understanding of cosmic history. If our universe emerged from a quantum bounce, then the pre-bounce phase had its own history. Did it undergo evolution and structure formation? Did it have galaxies, stars, planets? Or was it in a very different state, perhaps a hot, dense plasma approaching the bounce from the other temporal direction? We cannot know the answers yet. The time-reversed phase is not directly observable from our perspective. Any information about it would have been processed through the extreme conditions of the bounce, likely scrambling details beyond recognition. But the theoretical possibility that such a phase existed changes how we think about cosmic origins. It also changes how we think about cosmic futures. If the universe underwent one bounce, could it undergo another? Could our current expansion eventually reverse, leading to a contraction that transitions into another expanding phase through another quantum bounce? Cyclic universe models have been proposed before, but grounding them in the time-symmetric quantum structure offers a new foundation. These models remain speculative, but they are constrained by physics rather than pure imagination. They must be consistent with quantum mechanics, general relativity, thermodynamics, and observational data. They make predictions that can, in principle, be tested. This is what distinguishes scientific speculation from fantasy. The reinterpretation of the Einstein-Rosen Bridge exemplifies this distinction. Wormholes as cosmic tunnels were always speculative, never grounded in observations, always requiring exotic matter with properties never detected. The new interpretation is grounded in established principles: time symmetry in physical laws, quantum mechanics, general relativity. It does not require anything new beyond what physics already knows. It requires taking seriously what the mathematics has been telling us all along. This is often how progress occurs in theoretical physics. Not through discovering entirely new principles, but through understanding existing principles more deeply, applying them more consistently, taking their implications seriously, even when those implications challenge intuition. Einstein's relativity emerged from taking seriously the constancy of the speed of light. Quantum mechanics emerged from taking seriously the discrete nature of atomic spectra. This new understanding emerges from taking seriously the time symmetry of physical laws. The human mind struggles with time symmetry because our experience is so thoroughly asymmetric. We remember past, not future. We influence future, not past. Causes precede effects. This shapes our language, our thought, our deepest intuitions about reality. To imagine a framework where both time directions coexist as equally real components of a quantum system requires abandoning these intuitions. Yet mathematics allows us to transcend intuition. Equations can describe realities that evolution never prepared our brains to visualize. This is the power of theoretical physics. It extends human understanding beyond the limits of direct experience. We cannot visualize curved space-time, yet we accept it because the mathematics works and predictions match observations. We cannot visualize quantum superposition, yet we build technologies based on it. Perhaps we cannot visualize time-symmetric quantum structures, yet we may come to accept them for the same reasons. The challenge for physics going forward is connecting this abstract mathematical framework to concrete observations. Theory must make contact with reality. The time-symmetric interpretation must predict something observable, something that distinguishes it from alternative frameworks. Otherwise, it remains an elegant mathematical reformulation without empirical content. This is where the proposed signatures in the cosmic microwave background, in large-scale structure, in dark matter properties, become crucial. If any of these can be definitively detected and linked to time-symmetric quantum structures, the interpretation moves from interesting possibility to established theory. If predictions fail, the framework must be revised or abandoned. Science progresses through this cycle of proposal and testing. Ideas compete on the basis of explanatory power and empirical success. The time-symmetric reinterpretation of the Einstein-Rosen Bridge is now entering the testing phase. It has been proposed, its implications explored, its predictions articulated. Now comes the hard work of checking whether nature actually operates this way. The stakes are high. If confirmed, this would represent a fundamental shift in our understanding of time, gravity, and the quantum nature of reality. It would place time symmetry at the center of quantum gravity, suggesting that our asymmetric experience emerges from something more fundamental and symmetric. It would provide new tools for understanding black holes, cosmology, and perhaps even quantum mechanics itself. If refuted, it would still have served a purpose. Failed theories teach us about the constraints reality imposes. They show us where our mathematical extrapolations go wrong, where our physical intuitions mislead us. They narrow the space of possibilities, guiding future efforts toward more promising directions.